Artificial intelligence is rapidly transforming our world. From self-driving cars to personalized medicine, AI promises to revolutionize countless industries, but there's a catch. AI systems, especially the large language models like ChatGPT, are incredibly energy hungry. They require massive amounts of electricity to function, let alone learn and improve. This energy demand poses a significant challenge. Relying on fossil fuels to power the AI revolution would exacerbate climate change, a risk we cannot afford. We need a new energy source, one that is both sustainable and abundant. Could nuclear fusion, the energy source of the stars, be the answer? The quest for practical nuclear fusion has been a scientific marathon, not a sprint. For decades, researchers have pursued this elusive goal, enticed by the promise of clean, near-limitless energy. Now, with the rising energy demands of AI adding urgency to the challenge, could we be on the cusp of a breakthrough? The advancement of AI is inextricably linked to our ability to provide it with vast amounts of power. Training a single large language model can consume as much electricity as a small town. This energy consumption is only expected to grow as AI models become more complex and capable. Current energy sources are simply not sustainable enough to support the future of AI. Fossil fuels contribute to climate change, while renewables like solar and wind are intermittent and require large amounts of land. We need a new energy paradigm, one that can deliver clean, reliable power on a scale never seen before.
This is where nuclear fusion comes in. Fusion has the potential to provide a near-limitless supply of clean energy without the greenhouse gas emissions of fossil fuels or the waste disposal issues of nuclear fission. If we can crack the code of fusion, we could unlock a new era of technological progress, one where AI can flourish without straining our planet's resources.
Sam Altman, the visionary entrepreneur behind OpenAI and ChatGPT, understands the energy challenge facing AI. He has personally invested $375 million in Helion Energy, a fusion energy startup based in Washington state. This bold move is a testament to Altman's belief that fusion is not just possible but essential for AI's long-term future.
Helion Energy is just one of many companies racing to achieve practical fusion power. What sets Helion apart is its unique approach, which combines elements of several existing fusion technologies. We believe our hybrid design will allow us to achieve net energy gain, the holy grail of fusion research, within the next few years.
Altman's investment in Helion is a high-stakes gamble, but one with potentially world-changing consequences. If Helion succeeds, it could pave the way for a new era of abundant, clean energy, not just for AI, but for all of humanity. Nuclear fusion powers the sun and stars. It fuses light atomic nuclei, like deuterium and tritium, releasing enormous energy. Unlike fission, fusion is clean and virtually limitless. Deuterium and tritium can be extracted from seawater. Fusion produces no greenhouse gases.
Harnessing fusion on Earth is a huge challenge. We need to recreate star-like conditions. This means confining and heating plasma to millions of degrees.
The quest continues for a future with clean, limitless energy. Despite the challenges, researchers around the world have made significant progress towards achieving practical fusion power. Large-scale international collaborations, such as the ITER project in France, are pursuing magnetic confinement fusion, using powerful magnets to contain and heat the plasma.
Other approaches, such as inertial confinement fusion, use lasers to compress and heat the fuel targets. Helion Energy's approach is unique in that it combines elements of both magnetic and inertial confinement.
Their reactor design uses a magnetic field to confine the plasma while also using pistons to compress and heat it. This hybrid approach, they believe, will allow them to achieve fusion conditions more efficiently than other methods.
However, significant challenges remain. Maintaining stable plasma confinement at the temperatures and pressures required for fusion is extremely difficult. The materials used in fusion reactors must withstand extreme conditions, including intense heat and radiation.
And the economics of fusion power still need to be proven.
Section 6. A symbiotic dance. How AI can accelerate the fusion dream. Interestingly, the relationship between AI and fusion is not just one of energy consumption. AI itself could be the key to unlocking practical fusion power. AI algorithms can be used to analyze the vast amounts of data generated by fusion experiments, identifying patterns and insights that would be impossible for humans to discern. AI can also be used to optimize the design and operation of fusion reactors, improving their efficiency and stability. For example, AI algorithms can be used to control the magnetic fields that confine the plasma, preventing instabilities and disruptions. In this way, AI is not just a beneficiary of fusion power, but also a powerful tool for achieving it.
The convergence of AI and fusion energy represents a remarkable example of technological synergy. Just as fusion could provide the energy needed to power the AI revolution, AI could provide the intelligence needed to make fusion a reality. Section 7, a fusion-powered future utopia or pipe dream. The successful development of practical nuclear fusion would have profound implications for humanity. It would usher in a new era of energy abundance, freeing us from our dependence on fossil fuels and mitigating the threat of climate change. With near-limitless clean energy at our disposal, many of the world's most pressing problems could become solvable. Imagine a world powered by fusion energy. Transportation would be electrified, eliminating greenhouse gas emissions. Desalination plants could provide fresh water to arid regions. And energy-intensive industries, from manufacturing to computing, could operate sustainably without straining the environment. However, it's important to temper our enthusiasm with realism. Fusion power is not a silver bullet, and even if achieved, it will not solve all of humanity's problems. Social, economic, and political challenges will need to be addressed to ensure that the benefits of fusion are shared equitably and sustainably.
Section 8. Environmental implications, a cleaner energy horizon. Nuclear fusion is often touted as a clean energy source, and compared to fossil fuels, it certainly is. Fusion reactions produce no greenhouse gases, and the amount of radioactive waste generated is significantly less than that of fission reactors. However, it's not entirely without environmental impact. The construction and operation of fusion power plants will require significant resources and energy. The mining and processing of materials for fusion reactors could have environmental consequences. And while fusion reactions themselves are clean, the handling and disposal of even small amounts of radioactive waste will require careful management.
Despite these considerations, the potential environmental benefits of fusion power far outweigh the risks. By transitioning away from fossil fuels, we can mitigate the worst effects of climate change and create a cleaner, healthier planet for future generations. Section 9. Conclusion. The fusion factor in AI's destiny. The quest for nuclear fusion is a testament to human ingenuity and our relentless pursuit of a better future. If we can achieve this marvel, we will unlock a new era of energy abundance and empower the advancement of artificial intelligence. AI could be the key to unlocking fusion's secrets. Fusion could fuel the AI revolution. The journey is long, but the destination promises to be transformative.